So who wants a final exam? Raise your hand if you want a final exam. The alternative is you do SOTIs. Okay, so if we don't get that rate up to above 50%, we'll do a final exam. No, don't do it while I'm here. We'll take some time at the end. We'll take some time at the end. And that's obviously not a real threat, but you know what I mean. I'm not allowed to incentivize or disincentivize you to do SOTIs, but you know. Do you want a final project? Raise your hand for if you want a final project. Raise your hand if you want less work. Less work? Come on. What is this? Well, what I would want to do is I would want to hear about a planet that you created.
Yes.
That you created. So I would want you to demonstrate your understanding in this class by describing, what about your planet, like, is it big? Is it small? That leads to X, Y, Z, so on and so forth. Now, this could be an extra credit, or this could be a final. What would you prefer? But how many people have done the other extra credits? Because I'm not going to create an assignment that only 2 people do who already have A's. The other extra credit was going to the Comet, writing about the TikTok for haunted hydrology. Yeah. I don't know if anyone did that. I didn't see anything about it, so. Okay, I'll think about it. Another thing that I would like to point out is that we are very close to the end of the formation of the solar system. So that will happen on Tuesday. And then, wait. What's today? No, fuck, I'm bored. That's going to happen. This is all shifted. So we'll talk about formation today. We'll finish up formation here. And then we have potentially bonus lectures because you basically have nothing else. Right? And so you can decide if you would like to learn about exoplanets or if you want to learn about something else. I can give you some examples of topics, and then I'll post just like in the same module. I'll just ask you for your feedback as to what, like a ranked choice, what lecture you want for the last week. Because I don't actually believe that anyone retains anything they learned in the last week. But that's just me. So if you feel like you missed something in this class and you're like, I really wanted to learn about XYZ and then we didn't do it, my bad. Okay.
If aliens would exist, like, what's the possibility of that?
Well, I could give you an advertisement for a class that already does that. ASTR 3000 is life in the universe. It's for both majors and non-majors. So if you have a bio background, it's taught by a biologist, not a physicist. So it's like very much, where do you find life in the universe? But I could give you 10 seconds about like what the necessary conditions are. But you want more than that, or you want? Okay, all right. I'll think about it. A lot of people like life, but they like the idea of like life already coming here, like saving us. I don't think that would happen. Okay. I don't know if I already showed this image, and if so, I apologize for reusing images. What is this? Star. Star. You know what spacecraft took this image? AWST. Yeah. We don't use his name because he was an asshole. He doesn't deserve to have a spacecraft named after him. You can look it up, but I'm gonna say it. So what you're seeing here is a brand new star is carving out his home, blowing away the cobwebs that made the star, right? So if we could really zoom in here, we might be able to see a tiny little disk being formed. But I don't see one there because we're not zoomed in. Okay. We were going through this process of explaining everything that we found out in 13 weeks. And so far we have explained why everything goes around in the same direction. And we explained why there is big and small planets. Right? What else do we have to explain? So you have big and small planets. They go around the sun. Is that everything in the whole solar system?
How they form?
That's what we're trying to explain, right? Trying to explain how they formed.
Content of the planet.
Yeah, so we use the elements in order to describe like why there are two different types of objects, right? What about the small stuff? We need to describe why there are rocks that are rocky and why there are rocks that are icy, right? The rocks that are rocky we call the asteroids. Rocks that are icy we call comets. Good. Okay. And then we need to explain everything that doesn't quite look how we expected it to look. Think we can do that in one class period? Yeah, let's go. Okay. Come on now. Okay, we did that. Two kinds of planets. What was the reason why we have two kinds of planets? What? Yes, almost 100%. I would say 95% right. Yeah, you almost got it. You almost got it. Okay, so there, you're right. There was gas that was able to be gotten, but there's a step that we can't see anymore to go from the terrestrial planets, the rocky planets, to getting big enough to grab gas. Yeah, accretion, but of what type of object? Ice. We had to get out to where it was cold enough that you could accrete ice. Because in the inner solar system, there was no ice. It was all burned up. Right? Okay. Okay. So that's why we have two types of planets. Okay. My God, why is this not working? Okay. Oh, right away. Yes, right away. In fact, I told you this would happen. So I hope that you went home and you immediately studied and you were like, I'm ready to go. Okay. Remember the amount of building material present in the early solar system. 6% rocks and metals. Sorry, 0.6% rocks and metals, 1.4% ice, and 98% gas. How would things look if there'd been a lot more rocks and metal, 1.9%? The same amount, small amount of hydrogen compounds, only 0.1%, and the same amount of gas. Do I have to read that? Okay, all right. A large rocky planets close to the sun, a few small icy planets in the outer solar system. B, gas giant planets with rock metal cores close, gas giant planets with rock metal icy cores far. C, gas giant planets close, large terrestrial planets far, with the planet composition the same. D, large terrestrial planets close, small gas planets far, and E, no different than it is today. Okay, let's vote on 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, okay. So no one liked E. Anyone like D? Before you did. Large terrestrial planets close, small gas planets far. So if I increase the amount of rocks and metals, that would kind of make sense that you would have less gas or would it? No. Gas is still the same. Okay, so that doesn't change that. So if I had large gas planets far, then it wouldn't matter. Okay, so I can ignore this one. What about C? Gas giants close, large terrestrial planets far, so you switch their places. Still too warm for the gas giants. Okay. Even though we're made of rocks and metal? Right, but if I see what I'm asking in the question is take the amount of building block stuff, and instead of most of it being ices, turn almost all of it into rocks and metal. Does the question make sense now?
Yeah, and because they're able to get larger with that amount of rocks now, and maybe there are gas planets.
Ah, okay. So you could have gas planets close.
You have less ice to you have less to the almost no ice closer to the star.
Sure.
So you wouldn't be able to.
But is ice necessary in order to make a gas giant? Or is the size necessary in order to make a gas giant? It's the size that matters. You need to get to 10 to 20 times the size of the Earth. The only reason that doesn't happen in the inner solar system is because there are less rocks and metal. There happens to be more ice total. So if all of it is rocks and metal, then I can get large cores that can grab gas. That make sense? Okay. So now we're just between these top two. So now argue amongst yourself as to whether it's A or B. Don't do it so enthusiastically. Yeah,
Have you seen that nice? Yeah, ice stays the same. Gas. Ice stays the See earlier, looking back, I know, like, no, he can't even make political mistakes. But.
Okay, let's revote just between A and B.
I don't know.
Let's revote. Okay, final votes in 5, 4, 3, 2, 1. Okay. Has anyone looked at the homework for this week? Yeah. What is this?
One of the questions exactly same.
Exactly the same question, right? So should we talk about what the answer is? Or do you want to do it on your own? Oh, okay, let's talk about it. All right. All right, interesting. Okay, so let's think about the process. We claimed last week that the reason why the gas giants form at the distance that they form is because it finally gets cold enough for ices to condense to make large cores so that they can grab gas. Okay. If that's no longer a consideration and you have plenty of material to make a core, where would the first gas giants start? Yeah.
Where did we have to start? Because everything would agree there.
Yeah. You could get a gas giant at Mercury. Right? If you had this. So that means that I can have large gas giants close. Now, what's their core made of? Rock and metal. That's okay, right? And as I go out far, I get gas giants as well, because they do the same thing that they just did. But now it's mostly rock and metal with a little bit of ice. See? Could you explain that to a cousin at Thanksgiving in a week? Okay, well, you'll have to, right? Because I know that's the first thing that they ask you when you get home. How's your astro class going? Did you learn about the formation of the solar system? And you're like, yes, I did. Okay, so we just built the solar system. Yay! Okay, so now we have stuff left over. What's left over? What? Asteroids? Comets? Is that it? What about the gas? Where'd the gas go? How do we get rid of the gas? Okay, so we have this junk and we have gas. And we now have to figure out where it went. Where'd the gas go? And just around? Like right now? It's actually all gone. And I showed you a picture of this happening. Yeah, remember? So if we go back, we already have the answer. Gas gets blown away. Right? And every one of those, remember a couple classes ago, we saw those like little pockets that it blows. They all get blown out. Right? So you have a small window of time to build your planet before you lose the gas. Okay. So at the very beginning, young stars, they have a lot of stuff going on with them emotionally. And they're very hot and they're very explosive. And they start, really putting all of that into the universe. Okay. Hot massive star produces strong solar winds and it blows away the gas and dust. It leaves large solid things, planets, moons, asteroids, comets. Okay. And here's a hot star blowing on another star. This is several light years away, right? 1.5 to 2 light years away. So the fact that this thing is so warm is making this one evaporate. Pretty crazy. Okay. Then you have asteroids. We already saw that that's the leftover rocky junk, right? So these are the pieces of rock that did not form a planet. And they're mostly shepherded into this belt that we call the asteroid belt. And then you have the Trojans and the Greeks, the ones in front and before. You also have the Hildas, but we're not going to talk about that here. For the most part, these are just the rocky leftovers. And you have one big rocky leftover that's circular, which is what? Ceres, right? And why does Ceres live? It happens to be deep enough in the asteroid belt. It's not in resonance with anyone else. It's not in resonance with Jupiter. And it's in a fairly stable orbit that it doesn't get kicked too much, so it doesn't get torn apart. If I'm too close to Jupiter, I get kicked by Jupiter. Maybe I get kicked into the inner solar system. I hit the sun, I hit a planet. If I'm too close to Mars, I get kicked by Mars. Maybe I get kicked out and I hit Jupiter or Saturn, right? So slowly with time, you start with a bunch of little rocks. They smash into each other. They grind down. They become smaller and smaller. If they get too small, maybe they start getting blown away by the solar wind. If they decide they want to go into the inner solar system, maybe they get too close to a planet. They hit the planet. They hit the sun. If they go farther out, maybe they hit Jupiter. Okay. Okay. Comets? Mostly from the Kuiper Belt down here. And the Oort cloud. So Pluto, let's say it really didn't want to live its life anymore, could like put on the boosters and head towards the sun, and it would become a comet. What? Not a yeah, definitely not a planet. Well, it's a Kuiper Belt object, right? It's a dwarf object or dwarf planet. But it's very icy, right? The whole surface was made of like methane ices and water ices. So imagine if that like decided to come near sun. It'd be beautiful. The huge atmosphere as this thing sort of got really warm. It's not very big, it couldn't hold on to its atmosphere well. So if it gets too close to the sun, it starts to sublimate all that ice, turn it into gas, right? And then it builds this beautiful tail. And each time that it gets close to the sun, it loses more material until it becomes a little dingy rock that you won't notice. Okay? So there's a lifetime on comets too. These are the leftover icy pieces. We just saw the leftover rocky pieces. Come on now. The strange thing about the Oort cloud, so these ones, they make sense. They're in a plane. They're all going around. We haven't really talked about why these are all randomly going around in this big circle, the Oort cloud, right? So that's sort of a weird thing that we're going to put a small asterisk in. We're going to see if we can explain why all these comets are in a cloud. Because that's currently not explained by our theory, which tells us that everything needs to be in a plane, right? Everything forms into a plane, and this clearly doesn't do that. Okay. Hyperbelt, we're good with that. Okay. Oh, that's the same thing twice. Ta-da! We did the small stuff. Okay, what exceptions were there to the rules? And now we have to explain all the exceptions. What about exceptions to orderly motion? I just showed you the Oort cloud, right? That is not in a plane. So that's weird. Anything else? We talked about this like a little bit. Yeah, stuff rotating in a different direction, right? So we have, for example, even at Jupiter, you have the Galilean satellites. They all formed in a disk. But then you have like 60 other satellites that kind of just do whatever they want. They go in whatever direction they want. That's kind of strange. Okay. Anything else? Yeah.
Pluto's a little weird going like this.
Yeah, Pluto's a weirdo, right? Did you have one? Planet's tilt is a weird one, right? Why are we tilted? Jupiter's not tilted at all, by the way. Jupiter and the sun, they're pointing like basically identically like this. They're rotating. Saturn, almost exactly the same. Yeah. Venus is, but yeah, Neptune's also weird. It's like on its side, right? Okay, so all of these, oops. I got ahead of myself. That's coming, don't read it. All of these need to be explained by our exceptions to the rule, right? Because we can explain all of the rest of that. And maybe we already have an idea of where this is going. Okay, so which of these characteristics of Earth is so far not explained by our formation theory? Remember that our formation theory is that we start with a gas cloud. It condenses, depending on the temperature. Some of that condensation is rocks. Some of that condensation is ice. Then it adds small objects to become big objects. if you're big enough, you can grab gas from the disk, but you have to do it before the solar wind clears the gas out. Okay. So which characteristic of Earth is not explained by this? Is it that Earth is composed of rocks and metals? That Earth has oceans? That Earth orbits the sun counterclockwise? That Earth has very little hydrogen and helium? Or that Earth is located in the inner solar system? Nobody likes A? Nobody likes A. Okay, final votes in 5, 4, 3, 2, 1. Okay. All right. So we have a 3-horse race. Okay. C is in the front, and D and B are completely tied. Exactly the same number. So you need to turn to your friend, find out which of these 3 they chose, and argue for you, because you're obviously right. And make sure you can convince them of your argument. Okay? And if you haven't made a friend yet, you can turn around too. You can make a friend. And whenever you're ready, click back in.
Third grade mean like the ocean, they have to spell ocean.
Okay, I don't think you were very effective at convincing your friends. I wish I could show you the distribution as it comes in. That would be fun to do. This one's still winning. And it's wrong.
That's right.
It's wrong. It's wrong. It's wrong. Okay. This characteristic of Earth is explained by the fact that it goes in the same direction as the sun spins. So remember that we have this nebular theory. You start off very far and it collapses and it pulls in and it spins faster. So as everything begins to spin faster, it still retains the direction of the original spin. Okay, so you have this whole thing is spinning around. You snap off a little bit, it's going to be spinning in the rotation direction that it was already going in. So this is actually explained. Right? The weird one is the one that's spinning the opposite direction, like Venus. That's a weirdo. So that is not explained by the nebular theory. Okay, so now we have a problem. Which of these two?
You should let us discuss it.
Let us discuss again. All right, go. Okay, revote when you're ready. Dead time. Keep voting, keep voting. You get it wrong, we have a final for the people who picked the wrong one. Okay, all right. So people switched to E because I said that. Okay. So we think that Earth has very little hydrogen and helium gas is not explained by this process. So does this process explain why Earth has very little hydrogen and helium? You think it does?
Yes.
And the question is, which characteristic of Earth is not explained by this phenomenon? Okay, so we're just making sure it's a double negative here, right? Okay. Because
I was gonna say because reason I didn't pick D.
you didn't pick B?
I didn't pick B. I picked D because we're not the only body with an ocean. Europa has like they think that it has ocean under its. So like Europa.
Sure, but this is a characteristic of Earth, right? What characteristic of Earth is not explained by this so far? We do also have to explain why Europa has ocean, but that's later. Right, one thing at a time. So do we like D? Like civil war in this room. Okay, so Earth has very little hydrogen and helium because it's one word and it starts with small. Small. The Earth is small. The Earth could not grab a lot of hydrogen and helium. How big do you have to be to grab a lot of hydrogen and helium?
Very, very big.
10 to 20 times larger than the Earth. The Earth is not 10 to 20 times larger than itself. So it was too small. So it could not grab gas. So this is explained, right? What isn't explained is why the Earth has oceans. Why does the Earth have oceans? We have talked about it before, but this process here does not explain it yet.
Yeah.
Right? It's obviously explainable. Okay, so you saw this, right? We talked about smacking stuff. We have all this leftover junk, and we have the planets, and now you have 4.5 billion years to let them figure themselves out. Okay? So if you imagine that the Earth started with liquid oceans, right after it formed, those liquid oceans would have to sit on hot magma. And water and magma don't mix. You get steam, right?
Yeah.
So steam is a greenhouse gas. You would have a big problem, right? There was likely no water on the surface of the Earth when it was still hot from accreting. You would have this huge magma ocean, no ocean. Okay? Then it cools, it becomes hard. And once it's hard, it's dry and barren. Maybe some volcanoes going off, but at least you have a crust. And now you start smacking it with stuff. And that stuff that you smack it with is filled with ice. So you gotta do it a lot. And you gotta smack the hell out of the Earth, right? With a little bit of ice, because remember, those icy comets, 5%, maybe 10% water ice. So mostly you're just smacking them. But of course, there's just a little bit of water on there. Tiny, tiny bit of water, right? Just covers the surface, not deep inside. Okay. This period of frequent collisions, it's like the cleaning up part of the solar system. It happens like in a very quick time period. So you're getting like normal hits, normal collisions, and then all of a sudden you get this period of really, really intense collisions on all of the bodies. So we see that in evidence on Mercury. We see that in evidence on the moon. We see that the Earth, like when you look at the climate history of the Earth, right? This is a period of heavy bombardment. We think, okay, something weird happened. We're going to put another asterisk in that. Try to see if we can explain what the hell happened. Okay. We talked about this one, Uranus, not Neptune, sorry, knocked on its side. We talked about Venus spinning backward, right? We talked about Pluto may have been, come on now. Why is this not working? There you go. We talked about why Pluto is weird, sitting on its side and has all these near neighbors. Oh my God. And then we also talked about Mercury's large core. Okay. So maybe this all happened at once. Maybe all of these events are related. Conspiracy. Right? Is that an Illuminati for space? No. In fact, there is evidence to suggest that maybe the planets, when they formed, were not exactly where we find them today. Okay, what do I mean by that? There is a model. Oh my God, oh, this is why. Pop up. Okay. There is a model called the Nice model. It's spelled Nice, but it's the place in France, Nice. There's an observatory, by the way, best job, right? You get to live in the south of France. You do space all day. It's pretty cool. So what they did is they demonstrated that, so this is a simulation, and we're going to talk about it, and then we're going to play it. They simulated what would happen if you start with the giant planets. So the red one here is Jupiter, then the whitish one is Saturn, then you have Neptune and Uranus. You'll notice that I said that backwards. Okay? And then all of these green dots, that's the Kuiper belt. Because basically what they were finding is when they started doing simulations of the early disk, they found that the disk was very compact. That they couldn't understand how Pluto got out to be so far, why the Kuiper belt was so far away. Because every time that they tried to look at these disks, they would all be very close to their star. And they were like, huh, something weird is going on here. So they start simulating how Jupiter goes around, goes around, goes around. And they find out that the planets, they like to move a little bit. Okay, so they're interacting with gas. And as they're grabbing gas from the disk, their orbit changes. They grab too much gas, they move inwards. Okay? And what happens here, I'm not gonna be able to point to it, but you'll see it. This inner ring is gonna get a little contracted. You won't see it very well. And it's gonna go into resonance with Saturn. Okay? That's a problem. We saw what happens to, I think, we saw what happens to, yeah, the 10 is also in my office.
Oh, okay.
We saw what, yeah.
Maureen's office?
Yeah, right. We saw what happens to resonance in the asteroid belt, right? If you get into the 2-1 resonance with Jupiter, you get kicked out, right? Now, Jupiter can't get kicked out. It's bigger. It's a big old bully, right? But all of a sudden, they start interacting with one another. And they fuck up the entire solar system. Okay? I swear to God, look at this. Look at the time period. 100 million years, everyone's happy. Stable family, right? You get to 880, there's a little bit of tension in the family, okay? You can see that Uranus is kind of getting distant, right? And as it does that, it's kicking out the Kuiper Belt. The Kuiper Belt used to be more in, and now it's like shepherding it. It's like pushing it out away from its parents. I'm anthropomorphizing my community. I shouldn't do that. And within 3 million years, 3 million years, they switch places, and the entire inner solar system is just scattered. Okay, so this gives you this short period of chaos that we need for the heavy bombardment, right? It also may explain a number of things we've seen, right? How can you get a planet as big as Uranus tilted? I don't know. How do you get it to switch places with its friend, right? You got to have a lot of energy. You got to take that energy from these larger planets, Jupiter and Saturn, and these interactions that happen over millions of years, right? Let those resonances build up in order to change the entire planet. That makes sense? Do you believe the story? Other people do, so it's okay. Let me show you how it works. This better work. Oh my God. Hold on. Oh my God, hold on. We can do it live. If you type in nice model though, surprisingly, it's the first thing that comes up. Okay. Okay. All right, you can see this, right? Okay. So we'll go through this a little slowly. That's the start of the solar system. They changed the colors on us here, but we'll be fine with that, right? Okay. Note the original starting positions. Where is Jupiter today? Anyone know how far Jupiter is from the sun? Here is 10 AU out here. That's about 5 AU, about right. Here's the edge where Uranus is, less than 20. Can anyone look up where Uranus is today? Right. 19. And where's Neptune? 30, right? So this blue one, definitely in the wrong place, right? It's supposed to be like out here, big old circle. So the whole inner solar, oh, sorry, not inner solar, the whole outer solar system is too compact. Okay, so let's see what happens when you simulate all of these objects' orbits for millions of years. Okay, so you'll notice a couple things happening right away. You start with a nice, tight, compact Kuiper belt, and you get some scattering. So some guys are just going to get too close and they want to come explore the inner solar system. And then maybe they get close to Jupiter and they get kicked out. That's going to be a theme today. Okay. Or maybe they hit and they're removed from the simulation. So it looks really nice and green there, but the green density is going to go down. Okay. So you get some wobbling. You see the wobbling between Uranus and Neptune. Not really that big a deal. You can't quite see it here. But Jupiter and Saturn are moving. Okay. And as that's happening, you're getting more and more space between the inner solar system, or the inner two gas giants and the outer two. And let me just get it. Oh, okay. Hold on. I'm going to have to scrub here because otherwise it's going to go too fast. Oh God.
Video at the lowest speed,
Is that?
found here in the bottom right of the video.
Oh, this one. The word gear. Okay. Okay. Let's go to 0.25. Let's go. Oh, of course it doesn't have the intermediate frames. It's like one frame at a time. Okay. Okay. Yeah, so now it actually pauses to show you before and after, right? So let's just go back 10 seconds here. Is it running? Yeah. Oh, there you go. Let's go back. Let's go back. Okay, so let's see what happens. First thing that's going to happen is you get into resonance with the inner two gas giants, and then all of a sudden you kick the closest gas giant, and that's basically the big problem. Okay. Is it running? No. Okay, there we go. Okay. And then you see this here, the purple guy? That's the problem. The blue guy? That's the problem. Yeah. And there you go. So now they switch places and they start scattering all of the Kuiper belt. They create a population called the excited population. And that is because they scatter them and they force them, instead of being in a plane, they force them up and out of the plane. And they disperse a lot of the Kuiper belt objects. And then the two inner gas giants, they start playing well with each other. They don't get into resonance again, which is very convenient. And instead, they're just gonna, Jupiter's gonna go back to being in charge, and Saturn's kind of just adjust to this new norm, right? Meanwhile, the entire Kuiper belt is now scattered far beyond 30 AU, which is where we find it today, right? We find it like 50. Okay. And that happens very quick. Questions about that? Yeah. It might have. So one of the coolest things is that we don't have a surface for either of those objects, right? So we currently think that there were 4 gas giants to start with. You could have had a 5th. We could have also lost a 5th. So there is a whole different, I don't have a lecture for this because I wasn't prepared to talk about it, but essentially, as Jupiter comes in, the whole inner solar system moves with it. It's shepherded inwards. And there is a hypothesis, it's called the grand tack. If you know sailing, you know tacking, right? It goes in and out. So Jupiter came in, tacked, and then went back out again in order to do this. And there's a hypothesis that says there's probably a planet that existed in front of Mercury that got gobbled up by the sun, right? And this is one of the reasons why Mercury has such a shitty life, no mantle at all, just crust. Probably got smashed to smithereens during the grand tack. Right? We have what we have today, right? And we can measure certain things. Like if you have a rock in your hand, you can look at the isotopes and find out exactly how old it is. If you have a bunch of gas in your hand from Jupiter, you can't tell how old the gas is, right? But you can do other things. You can see how similar this piece of gas is to the solar nebula. You can see how similar this piece of gas is to the ice that we find in nearby, like Kuiper belt objects, and you can make some inferences about them. But can we say for sure that there isn't another planet out there that used to be part of us? No. And in fact, some people are looking for something called Planet X, which is bullshit, but that's my opinion. So there's a lot of people who like to debate about this. And in this process, they say, well, maybe there was a fifth gas giant and it was flung off. And it's just like still going around the sun, but just like really far away. And like space is dark, right? So if it's far away, we won't see it. But there are people who claim that the small changes in our orbits cannot be explained by only the planets that you see today. In fact, that was how Uranus and Neptune were found in the first place, because they are not visible to the naked eye. You had to have telescopes. So someone sat down and calculated Saturn's moving in a weird way. They had gravity, they figured it out. Newton figured it out in the 1600s. Telescopes happened in the 1600s. And they're like, go look in this part of the sky. And they found Uranus. French people with telescopes, right? That's how science gets done. So right now they're saying, hey, I think there's some weird stuff in the map. Go look in this part of the sky. There's one camp that says, that's bullshit. You guys didn't do your math right. And there's another one that says, we're looking. We haven't found it yet. I don't think it's there, but we'll see. I've been wrong before, just not today. Cool. Any questions about this? Here's an example of Phobos and Deimos. Yeah.
You don't believe an extra planet, but is there a possibility that one planet was out there and got launched so far that it's just completely gone?
Yeah. Maybe not. Maybe not planet. It's hard to say. So we do get on minimum one interstellar visitor per year. So there is a comet called Oumuamua, which is the first comet that we've ever seen from another solar system. Came in, like went near the sun and then flew out. Looked like a cigar. Everyone thought it was an alien spaceship. Comet. And the calculation is that we should get about one of those per year. The only reason we saw this one is because we had enough telescopes looking at the sky at all times to see them. So they've been happening for billions of years. We just haven't looked.
How do we know it's from another?
Yeah, we can like watch its trajectory. And then with math, we can figure out where its trajectory came from.
It just wouldn't make sense for it to be in our.
It's not possible. Yeah, it's on a trajectory that can only go in and out. It doesn't go around the sun at all. So it had to have come from somewhere else, right? So to your point, like maybe a planet did that, just got yeeted out, right? It's an unscientific question, right? We certainly know there are stuff called rogue planets, which are planets that may have had this happen in other solar systems. And then once they're not near star, they're not illuminated. So they're just left to do whatever, right? Okay. But okay, answer? We'll get that. Here are two captured asteroids. Probably. This is Phobos on the left and Deimos on the right. You know your Greek mythology. You know that Ares is the god of war, Mars is the god of war. So on the left is the god of terror, and on the right is the god of fear, right? Or maybe it's the other way around. One of them is fear, when one of them is terror. And what? Oh yeah, perhaps. You can see here that Phobos is going to undergo some redecorating. So you see these lines along it? Those are tectonic lines, right? Are they? What are tectonics again? Yeah, surface moving, right? So this surface is moving. We're going to land a rover on it in 2028. That's the mission that I work for. We're going to go there. I'm not going to do it, but the rover's going to land. They'll drive around. And we ought to do this. We're going to bring some of Phobos back. And we're going to look and make sure that it's made of asteroid, because that's what we think. But currently, we think these lines on it are from the fact that it is getting closer to Mars and it's getting pulled apart. So just wait a short few million years and Mars will have a beautiful ring system you can go visit when you're a digital avatar of yourself. Yeah. So this one here, you can tell these are like not circular, right? They're not big. And they also just look weird. right? Not just their shape, but the composition looks like asteroidal composition from the surface. And we know that because we look at asteroids, we look at them, they look the same. They look like captured asteroids. So we did it, right? Yeah, okay. So we did all the exceptions to the rule? Anything I missed? Okay. Okay. Oh, again. All right. Which of the following observations? Now you're all scientists, okay? And you're the science editor for your local, whatever BuzzFeed article. And you're trying to see which one of these is bullshit. Okay? So which of the following observations is inconsistent with the theory of solar system formation as I've laid it out? A, we discover a new moon of Uranus orbiting clockwise as viewed from above. B, we discover a previously unknown large comet passing through the inner solar system. C, we discover another solar system with 6 planets, all of which are Jovian and closer to the relatively cool star than Earth is to the sun. D, we discover a rocky dwarf planet beyond the orbit of Pluto with an orbit that is nearly circular and in the same plane as the Jovian planets. We discover a small object orbiting the sun with the same semi-major axis as Jupiter, but density similar to known asteroids. If you need me to clarify any of those words or re-say the names. Does everyone know which way we rotate? As viewed from above, viewed from the north? Counterclockwise. Okay. Final votes on 5, 4, 3, 2, 1. Okay, interesting. Anyone want to defend one of their answers? Why 3?
Well, I thought this rush when you were saying that.
Okay, all right. Yeah, E, because, every other body has their axis all weird, except Jupiter, but it's because Jupiter is the biggest.
Mhm.
And if it's made of stuff like that, if it's made of stuff like asteroids, and it's so close, there's a chance it either get pulled in and broken apart, or just, be melted completely.
Mhm. I like the thinking. But let me just remind you of 2 special weird groups of rocks. Okay? The Trojans. They do have the same semi-major axis as Jupiter, but they just either trail or lead, right? And just weirdly enough, they can kind of stay exactly far enough away that they don't get broken up. But they're strange, right? You're right. If you get too close, you're gone. Okay. So not E. Yeah. Sure, yeah. So like the idea being like, okay, it's orbiting strange. Does the newness bother anyone? It's fine, right? It's like in the outer solar system. We found new moons of Pluto recently, right? Okay, so we're okay with the new part. It's just the orbiting part. But like we see a lot of weird orbiters in our solar system. So if we can explain like Venus, I think we should be able to excuse this guy, right? That's okay. With this nebular theory, because maybe it was a captured asteroid. Okay, that could be an explanation. So it's not A either.
D, because B, there are some comets that we still don't know much about, so there could be just another large comet that's just coming along we don't know much about. And then C,
But you picked B or D?
I picked D.
D.
I was saying-
So this one's inconsistent.
I think B, I think B can be explained as it's just another one that we just hadn't found yet.
Oh, yes. Okay, I see what you're saying. Okay. You're doing process of elimination.
Yeah, and
Okay, I thought you were trying to explain D. Okay.
And then C, we discussed earlier that if it's cooler, the distance where ice would form would be smaller, so you can have more gas giants closer to a star.
Right, so
So that one can be found.
okay, so you like this idea that you could have 6 planets, all of which are gas giants and all of which are closer to their sun than the Earth is. This is a pretty crazy one. This is the one that you're supposed to not be okay with. Okay, this one I think is okay because we were just talking about like Planet X, right? Maybe you could have something that got flung out to the outer Kuiper belt and we just haven't seen it yet, right? This one you're supposed to be weirded out by. Because 6 planets that are as big as Jupiter, how did you get away with that? Now you're right that being cooler helps. But it's still too close, right? I don't think that we think they could have formed there. And yet, we'll find out they did. Stay tuned. Okay.
Once they're Jovian, it's the big issue to them because they're so big.
They're so big. They're so big. That means that they have a lot of mass. That means that they had enough mass to grab gas from the disk, right? And we usually don't think there's enough mass to grab that much from the disk. Like if you look at the distance between Saturn and Saturn and Jupiter, that's like 2 AU, right? So we're talking about sticking 6 of them in a space that's half that big, right? That would be a weird thing to find. We did in fact find that, but it is a weird thing and it made us all very upset. Okay. All right. So if you think about the theory, you should be able to think about different situations. And you know me, you know that I will want you to explain your reasoning. So I will ask you annoying questions. Like, how would planets in our solar system be different if the nebula had cleared away before capturing any of the gas? Yeah.
Gas giants would be smaller.
Smaller, or what do you mean by that?
There'd be less gas, so of course the gas giants would be a lot smaller.
Yeah. So, what if they couldn't capture any of it? Well, what would you get instead?
Get a lot of terrestrial worlds.
Yeah, terrestrials, and then maybe in the outer solar system, you'd have a new thing, which is like a rocky terrestrial world with ice, right? So you can imagine like a super Earth with no gas. We kind of have to like stretch the imagination here, right? Because even if you had, remember how much more ice we have than rock? What's the ratio there? Yeah, it was like 1.14 and 0.6% between the two. So one of them is about twice as much. You have about twice as much ice as you have rock. Right? And so when we want to explain something like Europa's oceans, that could be a potential explanation, right? You just have icy bodies there as long as you can get them cold. If you had something that was maybe 10 Earth masses and 60% of it is ice, can you even imagine what that would look like? Be kind of cool. It'd be like you have this like icy object at the top, and then you have like underwater region, and then you have rock all the way down. Okay, I'll make a picture for you. Okay, so you should be able to answer that. You should be able to answer, hello, how the solar system would have looked if ice condensed at 50 degrees instead of 150. Yeah.
Gas range. You shift it over a little bit.
Which way? In or out? Out, right? Because it would take, you have to go out farther to get colder. So the frost line would move out. Similarly, if I made this hotter, frost line would move in, right? Okay, or how would the planets be different if the whole nebula had cooled below the condensation temperature of hydrogen compounds before you started clearing off? And if it was cold from the very beginning all the way out. Snowballs that lead to before the solar wind clearing, like how would the planets be different? Gas snowballs all the way down. Right? That makes sense? Okay, we need a little bit of creativity and we need a little bit of argumentation. And we're going to add those two together in our homework. I know you hate that, but that's okay. So when did that all happen? Yesterday. Actually, I was not born yesterday, so that's incorrect. Recently? No, I was not born yesterday. Oh, I was. You remember this thing? All right. So when did this happen? Long time ago. Correct. Correct. Anyone more specific? Okay. Okay. I like that. 4 point. Okay. Let's ask a question. Well, don't give it away. Oh my God. Just trying to see who's paying attention. Okay, 5, 4, 3, 2, 1. Okay, almost everyone has it. It is, in fact, 4.6 billion years ago. Okay. How do we know that? Because it says right there. So I've never lied on a slide before, right? Why would today be the first day that I ever lied on a slide? Yes, but Big Bang, remember, is the creation of the universe. I'm asking about the creation of the solar system. What evidence? I mean, you can't trust me, right? I've tricked you all semester. You don't really believe that any of this is really happening. It's kind of come because it's a GE credit. So what is the physical evidence that we have that the universe or that the solar system is 4.6 billion years old?
Meteors.
Meteors? What do you mean by that? Rocks, meteorites, stuff that falls from space is 100% correct. Okay, meteorites, in fact, are the oldest rocks that we have. And they all, you know, if we keep looking at all this stuff that we've ever found, you can find stuff that's recent. You find some rock that's 1 billion years old. You find a rock. If you go into the ocean, you can find rocks that are like 20 years old, right? Like you go to Hawaii, that lava is brand new. So that's not helpful. The Earth is not helpful, right? There are some old rocks on Earth, but they are not the oldest rocks in the solar system. Because, like we talked about earlier, the Earth formed and it had a magma surface, which means that it formed and it had to cool down. So the oldest rocks that are possible on the surface of the Earth are after the Earth was formed. And I want to know when the Earth was formed. I want to know when the first rocks condensed into the disk. And that can only happen through meteorites. The meteorites are the leftover pieces that condensed but never burned up. And if we look at all of the meteorites, not a single one of them has an age that's older than about 4.6 billion years old. What do they look like? They look sick. Okay. So this is the 1969 Allende meteorite. So if you want to put some more digits on it, it's 4.567, and there are actually more digits than that. They're really cool. So you can look inside. You like, this is the rock. You like cut it, and it's made of like little bits of stuff that like get squished together. It's called composite rocks, right? It's not formed in a magma. It's formed by like just condensation and then sticking together. Okay. And then if you look inside of here, they have these little circular parts. And those circular parts give you a concentration of one element compared to another. In this case, we can use radioactive dating, not carbon dating, radioactive dating, to find out exactly how old these little bits are. And these are the oldest rocks in the universe, in the solar system. Okay. They tell you the last time, come on now. They tell you the last time that a star exploded. So like I said earlier, we're all made of star stuff. This is the Crab Nebula. This is just an example of a star exploding and putting what it made back into the universe. As it does that, it creates unstable isotopes of iron, of lead, of plutonium. And they're unstable, they'll decay. And so they're going through that process, everything is fine. And then they get trapped into the matrix of a rock. And now, instead of being able to exchange with other things in the gas and dust, now they're trapped in that rock. And I can compare how many of the decayed products are there compared to how many of the products that it came from. So the parent versus the child. Right? Okay. You want to know how that works? Okay. Everyone stand up. Do you have a coin? No, we're just gonna do it. We're gonna do it by thought. Everyone has to stand up though. Okay. You are all going to be the parent nuclide, and you are spontaneously, you're gonna close your eyes. You're spontaneously, after I say 1, 2, 3, you're gonna choose to either stay standing up or you're gonna sit down. Okay? So close your eyes. 1, 2, 3. Okay, now everyone open your eyes and look around. Okay, so what happened is the people who sat down, they were the parent nucleus and they decayed spontaneously. Okay? So I could now count up who's left and I could see how many parents and how many children. So now we'll do it again. Close your eyes. Of the people standing, on the count of 3, you're going to choose to sit down. 1, 2, 3. Okay, now look around. Okay, so now fewer, right? But you can never get the kids to stand back up. Once you've made kids, that's it. Sorry, hold on. That's what I mean by that. Okay, so this process keeps happening. You can all sit down now, right? So this process keeps happening because at every stage, half of the parents become children. And then half of the remaining parents become children. Okay? And I'm not going to go through the whole thing because we don't have any time. But essentially what happens here is you start off with something like potassium. You know that your bananas are radioactive? Yeah. Do you know that it won't kill you? Okay. In fact, bananas are highly safe and doctors say, good for you. So you start off with one banana. And we'll think about the fact that bananas can sometimes I'm saying bananas, but I mean potassium, can sometimes spontaneously produce a noble gas called argon. And you can see that right here. Here's argon, and here's potassium. Okay? So potassium can radioactively decay to this one. And the only thing that changes, right? 19 to the 8. Okay. So interestingly enough, potassium, you find it in minerals. So you find it quite often in crust, but argon is a gas. So potassium might be entrained in the rock somewhere, and then all of a sudden you have little tiny argon gases. And argon hates participating in chemistry because it's a noble gas. It thinks it's better than everyone, right? It's part of the, okay. So there's a decay life. And if I compare how many potassiums I have to how many argons I have, I can figure out how long that rock has been sitting there. It takes about 1.25 billion years for half the potassium to turn into argon. For you guys, it took like 40 seconds for you to sit down, right? But that process is the same thing that happens inside of a rock. Spontaneously, atoms in the rock will just decay. And very good scientists come along and they count them, and then they figure out how many daughters and how many, or how many parents and how many children there are. Right? And from that, we can figure out the age of the rock. That make sense? Okay. I don't think we'll do any math about this, but let me show you the oldest solar system rocks. The oldest Earth rock is about 4.4 billion years old. The oldest moon rocks that we can find are about 4.4 to 4.5. Yeah. I'm gonna ask a geologist. It's like a mineral. So it's like it's called zircon, and it's like, I forget exactly what it's made of, but you find them in Australia. Australia is one of the oldest continents, and this is like a tiny piece that's formed inside of other rocks. They're called zircons. You may have heard like zirconium, which is like fake diamond. So I don't know. I actually can't tell you why it's blue, but that's what that is. Oldest moon rocks, 4.4 to 4.5 billion years old, and the oldest meteorites are somewhere between 3.53 and 3.576, blah, blah, blah. I rounded, but you know what I mean. Okay. That's more or less right. So we'll talk about the stages of the solar system on Tuesday, and then you'll have Turkey. Think about what you want to learn. I'm going to post a little Google thing. And then fill out your SOTIs, or you have to take a final. I have an answer.
Okay, so,
I think maybe.
this sucks because I just was last Tuesday for the last